Hello. Today we're going to be discussing new subject here after we've learned PEMDAS. We're going to first quiz you guys on the ability to do multiplication tables. So we're going to do first quiz, alright? 12 times 11 do 6 times 7 8 times 9 do 5 times 7 do 7 times 7 7 times 8 11 times 11 12 times 12, and that's about it. That's all you guys are going to be doing. Alright, so let me know what your results are. Alright, 12 times 11 be 132. 6 times 7 is 42. 8 times 9 is 72. 7 times 7 is 49. 5 times 7 is 35. 7 times 8 is 56. 12 times 12 is 144. And 11 times 11 is 121. And that's all there is to it. Alright, now we're going to be moving on to the rest of the lecture here. So all we're going to be doing today is discuss this little funny symbol here. Yep. Believe it or not, we're going to be doing this for a little bit. That is called the square root. The square root of something. We must first understand when I said second power all less time ago. So let's go back to what we talked about exponents in PEMDAS. In PEMDAS, the E is standing for exponents. And we last discussed, we discovered that exponents are a form of parentheses with a multiplier onto them. A specific multiplier of itself. So let's just put down 5 times 5, and let's put in the exponent of 2. So the way you say this is 5 times 5 within parentheses to the second power. Now I say second power. Let me write this better so it actually also let me expand my canvas real quick. I say second power, but really you should treat it as the phrase squared. We're actually dealing with 2 dimensions in this case. I could try to give you a physical example of what this exponent kind of looks like, what it represents. We're talking about a perfect square, where both the height and the length are equal to each other. So h is equal to L in this case. They must be in order to be a perfect square. And also to be a perfect square, it needs to have 90-degree angles on all sides. Which is essentially going to do, it's going to be lining up the 5s like so, as I did previously. Into a grid-like structure. All these units line up to be a perfect square with 5 on the top and 5 on the side. And this all gets closed in. And we can discover our answer there. This 5 times 5 is actually 5 to second power within another second power here. It's actually 5 squared. This is a nice little example, and there's a lot of fun things you can do with this. And by fun things, I meant like fun math things. You know, maybe math isn't all that fun to you, but to me, it kind of is, to some extent. I mean, it can get boring if I'm doing really long problems, and I'm like, oh man, this is so long, this is so tedious, this is so annoying. Can we just do the fun part where it's like a cool concept to talk about, like zero? Zero's so cool to talk about. I like talking about zero. Zero, zero has a lot of potential, and it's hard to really find. It exists, but it's hard to find. Like infinity. Infinity is not. And before I go off topic or go on a tangent, no pun intended. Let's continue here. So 5 times 5 is 25. 25 squared. I previously said that 5 times 5 could just be 5 squared. I mean, 5 to the second power, either or. And what I meant by that is that when you square things, you're actually arranging them in rows like this and making a square out of it so that it actually does match the shape. This is 5 on the top. This is what? 7? Did I put 7 here? I actually forgot how much I put. It's 7. Yeah, so 2 more. Alright. So yeah, that's just as a square example there. What we're doing here with 25 is exactly that same case. Or you can just say we're doing 25 by 25. 25 times 25. You go to the store and you see those lumber pieces of lumber, and you just look at what they say and it says 4x4 or 4x2, and I'm like, what is that? No, it actually means it's just multiplication. It's talking about its dimensions. Yep. 4x2. It's height and length. So this is actually just a very simple problem. I mean, not that it is meant to be super simple. I mean, it's essentially just 20 times 20 times, I mean, plus 5 times 5. I see it as that, but 25 times 25 to me is something that you could figure it out on your own, something that you could feel for your own, but I can't really describe that any better than that. Also, I lied. It is not that. I just remember it as 625 for some reason. Oh, that's weird. I could have sworn. No. No, that's wrong. No. I think I am right about something here. It's about something here. Are there 5 more 20s? No. It can't be. You know what? Just keep it as 25 plus 25. No shortcuts involved. Just right now focus on the fact that this is equal to 200 and 220. I mean, 625. I keep on saying 200, and I don't know why. 200 is nowhere to be found here. This is the answer. All right, 625, 625. All right, that's the answer to this. All right, this is all arranged by a length and height of 25. This is a perfect square. It'll be a perfect square. It always will be. I mean, I draw it terribly, but I have the shape tool here. Why don't I just do it like this? That's not a square. That's not a perfect square. No, this canvas is a perfect square. Yeah. Canvas options. This canvas is 2,000 pixels in width, 2,000 pixels in height. It is a perfect square. This is a good example of a perfect square. It may not look like a perfect square because maybe our monitors are different, but no, you should know that it is a perfect square. This is 100% a perfect square. There's no way it's not. Anyway, yeah. So there we have it. We have an example of a perfect square. Let's just say, yeah. Where is it? Oh my god, I'm already forgetting how to use this. Alright. So let's talk about what an example of a perfect square would be. Let's do another problem. Let's make it simple. Let's make it 400 times 400. let's say there were 400 pixels of all of that cubed, right? Or not, yeah, not cubed, squared. Right? This is what it would look like. 400 times 400 look like this. Yes, it's a perfect square. This is 400 times 400. Another 2 zeros to add on. And there you go. There is our answer to this problem. There's exactly 160,000 pixels within this white square, with 1 pixel being this right here. This is 1 pixel. Do you see it? Yes, they are all perfect squares. This right here is a perfect square. This is all perfect square. So let's. Do you have any questions? Do you not understand this still? This is something that might be a little bit difficult to understand because I'm not explaining it well. So I will definitely respond to questions on this one. Yeah, got questions on me describing this and my inability to say so very well. Do let me know. I will try to answer a little bit better, but you gotta describe where you're stuck on here because I'm not very good at interpreting questions when it comes to like saying how did you get from there to there. And that doesn't tell me a whole lot. Maybe say, okay, maybe I'm not understanding how there are a bunch of tiny little squares within all of this white spots, and you can place a tiny little square in each one of these. I'm a little bit confused on that. Why does that relate? Well, I can tell you why it relates. Because you go in the corner here, right? And you go to the other corner here. Whoops. Go to the other corner here. These black dots I have placed in the corners are nothing more but the designated end areas of this square. Each side is 400. 400, 400, 400, 400. That is how many little tiny squares of those black dots I placed. Those black squares, actually. They're not really dots, but they look like dots from far away. You can fill 400 on each side, and 400 in each row. I mean, on each column, and in each row. You make like a little miniature grid. We can make this a lot more simpler if I just explain it. Or something even smaller. Let's go to 20. Down to 20. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And if you keep on going, this will always be 20. There will be 20 on each one of these rows. And we're going down 20 times. This is a perfect square. And of course, as I said, going down, you can do it from side to side using columns, which describe up and down. north and south. And you go to the right 20 times. This proves this is, in fact, a perfect square by eyes. Whoops, messing this up. But you get the idea, don't you? Of course. So let me just fill it in all. Thank you. Yep. So, anyway, that's how this works. Back to 2000 by 2000. Okay, so now let's explain this kooky symbol right here. Very weird, very crazy. What could it possibly do? Well, as I said before, this is the square root. This is what is holding up the tree. That is the perfect square. The root of it. The root cause of how it is formed. Remember when I said that you need to have those little rules telling what's happening here? See, the roots of a number would have to be this little dimension. 625 square root is 25, because 25 times 25 gets you 625. This is the square root. This is the root cause. This is what makes it happen in the first place. If you get to 25 pixels across and down, across and down, then you will get 625 pixels within this perfect square. It's when you have 625 total pixels, it's asking you, what are those little square parameters? I mean, you could still put a number in there that doesn't make a perfect square, and you'll get a weird answer if you plug it into your calculator. This is not something you can do, you can solve without a calculator. This is something that you absolutely must use a calculator for. So for example, let's do the square root of the number 2. Yes, this is what the square root of number 2 would look like. And you can clearly see it's only going up by 1, but going down to the right by 2. It's not right. How is that possible? This can't be a square. It's not a square. This makes no sense. But yet, if you plug it into a calculator, you'll get something very, very bizarre. You'll get a very, very long chain of numbers following a whole number of 1. So it's 1.4, 1, 4, 2, 1, 3, 5, 6, 2, and so on and so forth. It's an infinite chain of random numbers. But those random numbers will always be the same if you plug it in. I say random because there's no pattern going down. There's no real calculation here. Except there kind of is going on, something going on down there. I'm just not at that level to tell you what that is. I can only tell you this much. Going down that chain of trying to figure out where it is, it's like trying to do some very weird shenanigans of trying to make it look like a square, where you're going around saying, actually it kind of looks like a square if you do it like this, but you gotta cheat at the system just a little bit, saying, oh well, you know, we could have space here but there isn't, and oh well, I guess it's not, so you can't do that. So no, it's a weird number. If you see this, what this is telling you is that there is, in fact, an understood root cause to cause this square, but it is hard to find. By multiplying that number by itself, you will get its number, or close to it. This is defined by a rule where if you take the square root of a number, any number really, and multiply it by itself, you will get the number within the whole box. So the square root of 4 times the square root of 4 will just be 4. So when you have numbers like this, square root of 2 and square root of 2, believe it or not, the answer will be 2. Even though it has a very weird result when you plug them in. It is in my opinion that if you have these numbers, you should keep them in this square root form, also known as the radical form. The square root symbol is not actually called a square root symbol. It's actually abbreviated, not well abbreviated. It's kind of just like a nickname for it. What it actually is called is a radical. A radical has a understood parameter over here on the left. If you write nothing, you will get an understood parameter of 2. But you can define its parameter by anything, really. By 3, by 4, by 5. And basically what this tell you is, oh well, we want to make this a cube. We want to understand the cube root of it. We want to understand the 4th root of it. We want to understand the 5th root of it. And I say the 4th and the 5th after cube because, well, we don't know anything past those dimensions. I'm going to be honest. We've been using 2 and 3 as our little dimensions for our space. Let me get into something kind of cool as a little tangent. You don't really have to worry about this too much. This is just going to be me talking about something that I think is kind of cool. Let's say we have a little box here. Yes, a little box. A little box that we can see through. It's a nice cube. You can see its form and everything. Right? This little ice cube. Just make it look a little bit better. Don't mind me. We're gonna get rid of its insides actually. Let's make this an actual just a regular cube. We're gonna kill the insides just a little bit so you can get the illusion of it actually being three-dimensional. No, let's not do that at all. I have a better idea. Let's do this instead so it looks much more right. And now we're gonna have to erase this. Don't worry, I'll get to my point in a bit. Let me just do my little fancy project here. Doesn't it look like a cube now? Doesn't it look like a little cube? Yes, it does. Now let's color code it. Where these sides represents depth. This side represents oh, let's not use that color. That color is funny. Let's use blue. This color represents length. And this color right here represents height. There are a bunch of this little top side of this cube within the cube going up and down. So you can visualize this by me doing this. By essentially just copying this. Let me just get rid of this part here so you can look at it better, a little better. This is one slice of it. You can keep on taking little slices of this off until you have well, reached this point down here. So let me just do this real quick. Alright, this will have a point very soon. Oh, would you look at that? It fits. Look at that. Look at that. Yep. This little piece, believe it or not, actually fits here. This is the yellow. This is height. You can see that we took a little piece off of it. A little piece of it. And we can place it within the middle. This is how it represents the height. So let me just take this real quick. Oops, that's not it. So let me just compare these side by side real quick. Do you see how the yellow represents the height now? Do you see how this yellow goes in and out? It is essentially just me extending the shape. Here, let's do it like this. Whoa, whoa. This represents the blue. We'll talk about this. The blue is, well, no. This represents depth. Which, yeah, I guess it would make sense to call this blue as you're going in and out. My bad. The blue is depth and the red is length. My bad. Then we have, what's it called? The deal with the red here, where it looks like it's actually going side to side. So a little cube here is going that way, and the little yellow is going this way. It's going up and down, left and right, and then we have depth here. Yes, believe it or not, it's just how it goes. Isn't that kind of cool? I'm doing a little bit of geometry here, but just gotta focus on the fact that there are a bunch of miniature blue squares just like that, where if you cut just like this and you apply it to the point here, you'll be able to see that there's blue within this, and there's red within the sides here. I can cut this here, pick that red, put it right here, and then write the space there. And you can see how it works. You can test it out for yourself if you want. This is very fun to mess around with, and you can see the dimensions. It is better off explained by playing games that are in 3D, like Minecraft, for example. You can see the X and Y and Z coordinates by hitting the F3 key, and you can see a lot of things that weren't really described very well by me. But my point of this being is that there are essentially three things you're multiplying here in this cube. You're multiplying a depth, which we'll call W, because really it's just width, length, and height. To correlate with this, I'm going to color them the same thing so you can see them. This side here represents height. This color here represents width or depth. And this red color here represents length. This is the direction, this is the flow of it all. This is where they go. They go in this direction. They go up and down, side to side, front and back. That is the direction that they go. There are only 3 total axes in total. Our universe is made up of those 3 directions. So when you tell us to do the cube root of something, you're trying to figure out what all of these three elements are within a problem. So let's just do something that is basic and trivial that everyone can know. 256. Yes, 256 is a number. I think at least 256 is in fact a number, but does it exist as a cube root? No, it does not. No, it's a square root. No, that won't work. Let's do 4 times 4 times 4. Yes, 4 times 4 times 4. 64. Yes, that'll work. So let's say height, width, length are all 4. We have particles arranged in 4 here. 4 units of particles. 4 units of particles going up and down. 4 units of particles going left and right. And 4 units of particles going north and south. I say up and down and north and south and west and east as their own thing. A compass only shows you 2 axes, but saying up and down implies that there is another axis with height. You can apply 2 axes to anything depending on the situation, and it'll describe to you only the second powers. It'll describe to you the square root of things. It'll tell you that, hey, this is what this is. You have 2 5s here, 2 5s to the side. See, if I only have these 2 dimensions, height and width here, I'd only have a square. If I didn't care about 4 here, which I'll just circle here. If I didn't care about that, we wouldn't have that. We would just have this. But if I started doing more of these, I kept on doing more of these, and I kept on doing more of these, and I kept on doing more of these, I kept on doing more of these, I kept on doing more of these, so on and so forth, I'd eventually have some meaningful depth here, and I'll make a cube. Yes, this is a cube. It's very fun to do. So you can understand now, to some extent, that this is also a multiplier for this. You want 4 of those. You want 4 of those papers. You want 4 of those little slabs of units that are in space. It is all design. So, when I say to the 3rd power here, when I say anything to the 3rd power, and x is defying any number here, I'm really just saying we have x cubed. I mean, my bad. If I say x cubed, I'm really saying we have a shape here of a cube. This is a pretty poor drawing of it, but you get the idea. We have a cube here, and oh man, I really want to attempt it again. We have a cube here, and we want to find. We want to, what's it called? Make any number its width. Let height, width, and length. But when I say x to the 4th power here, can't really say it because we're talking about a whole axis that we don't really know of. And I'm just gonna start saying this right now. It's a lot more complicated than just saying, oh, it's a tesseract. It's a space within a space. A lot of people will say it's, you know, there's the 4th dimension, tesseract. You could do a little tesseract drawing right here to show you what they mean by that. That is a cube within a cube, where the cube outside gradually becomes the cube on the inside. They're connected at points in time. This is a very complicated thing, and no, you couldn't say tesurrected. That'd be pretty funny if you did, though. I like to see your math teacher tell you, hey, what the heck did you just say there? What you just told me? I bet your geometry teacher wouldn't even understand you either, because, well, that's not real. This is not real. Don't do that. Don't be smart and say, yes, I know about the fourth dimension. The fourth dimension is time. Don't do that. Don't do that. I did that, and I thought I was cool. I was lame. Don't do that. That's not fun at all. You don't want to be pointed out and say, oh, look at this guy. He thinks he's so cool, knowing all this fourth dimension stuff. Don't worry about it. It's not really important. All you need to know is the reason why I can say squared here is because we're dealing with squares. And the reason why I can say cubed is because we're dealing with cubes here. That's all there is to say on the matter, really. So anyway, let's go back to this square root problem now. 36. The square root of 36 is 6, because 6 times 6 gets you 36. Length and width. Length by width. This is 36 squared. I mean square root of 36. This is 36. I mean this is 6 squared. 6 squared. Square root of 36. 6 squared. Square root of 36. Now, this represents the pieces that make here. These are the roots. The little root that makes 36 here. From the understood to modifier here. That's about it. That's all there is to say on the matter. Really, it's just reverse multiplication. To some extent. It's just trying to find what number you used. No big deal. You could divide 36 by 6 to test it if it is 6. You could always just divide and say, does that make sense? Does this divisible by 6 and give me 6? Oh, well, it does. Okay, that's a nice little check there. But you don't want to do that. You just want to know this. Okay. So, now I have that. Now I'm going to make you do another quiz based on what I forced you to learn. You're going to do 3 times 3. And you're going to do 5 times 5. You're going to do 7 times 7. You're going to do 9 times 9. You're going to do 12 times 12. You can do 8 times 8. You can do 6 times 6. And 4 times 4. So right now, let's go. Let's take this right. Let's do this right now. All right. Pause. Because I'm about to tell you the answer in like 2 seconds. All right. This is 9. This is 16. This is 25. This is 36. This is 49. This is 64. This is 81. And this is 144. Okay. Now what did we just do? We just did some cubes. We did some squares. We did some squaring. Yeah. The tables I told you guys to do. Told you guys to learn. You ended up learning a little bit of square roots in a sense. You learned that the square root here is 5. The square root of 25 is 5. You learned the square root of 9 is 3. You learned the square root of 16 is 4. You learned that the square root of 36 is 6. You learned that the square root of 49 is 7. You learned that the square root of 64 is 8. You learned that the square root of 81 is 9. You learned that the square root of 144 is 12. Why? Because you did it backwards. You did it all backwards by learning these 8 numbers. So let's continue forth. I was also going to tell you the funny thing about square roots, and that is where if you had a situation like this, This is a little bit funky, don't you think? What is this number? What is this telling me to do? What is this exponent telling me to do? No, don't worry. It is just the square root of 9. That is the same as the square root of 9. A fraction exponent is nothing more than a radical. Yes, believe it or not. Where the one describes the exponent inside, which is 9 to the first power here. And it wants me to find the root of 2 here, which is the square root. There's an understood stuff here. So if I were to, let's say, write down 3 over 2 to the 9th power here. I mean 9 to the 3 over 2 power here. Then I'm just saying this. I want to know the square root, because this is a 2 down here, of 9 to the 3rd power. So that's kind of fun. I mean, now you can play a little guessing game, not guessing game, play a little reading game here, saying, oh look, there's a 3 up here, this is my square number, this is my square root number, I'm not my square, this is my radical number, this is my exponent number. So this was a 4, telling me to write down 4, and there's a 3rd right here. So x to the 3 over 4 power just gets us this down here. This is the exponent, this is the radical, this is the exponent. I mean, this is the index of the radical. This is the radical right here. This is known as the index over here. Yeah. Okay. And then we have to deal with this number here. For the first time, we have gone into negative territory. Don't worry, negative numbers are very simple. I'll explain them right now before we talk about this. So we have a number line going from from 0 to 3. But, you know, how do you go back from 0? What are these numbers over here? So confusing. Don't worry, you can think of them as numbers you're going to subtract. Or just think of it as another direction. A positive flow and a negative flow. Here it is. By going left, you're counting up, but with a negative number once you go past 0. Normally when you go left, you count down. Can you see that? But here you're counting up once you get past 0. Going past 0 here, you start counting up in a different direction. This is the opposite direction. It makes sense too, because if you started counting like this, you start saying, yes, -1, -2, 0. How did you do that? That makes no sense. There's no flow there. That can't happen. Let me tell you why. Because there's a flow for all numbers. You have a positive flow and you have a negative flow. And this applies to decimals too, where you count up the decimals. So -1, -1.1, -1.2, -1.2. You're going in a different flow. Just treat negative numbers as positive numbers with a minus symbol on them, and you'll be good in its own flow. So if you want a good, accurate representation, it's hard for you to actually get to understand it. You could just say, let's make the right side negative. Oh my God, my mouse is breaking. Let's make the right side negative temporarily so I can understand it easy. You can temporarily do that, but don't do this all the time. You want to understand it easy. So what would be the middle between 1 and 2? -1 and -2 would be -1.5. That's the middle in between those two. The middle number. Remember the number line thing? That's what I'm talking about. Okay, so now let's talk about this. -1 here. Yes, we have this issue here. Don't worry, all this is really telling us to do is do 1/9. It's a fraction problem, essentially. And I can tell you why in a second. Okay, actually, no, I should about mine. We're not going to learn that stuff, because that stuff is going to require us to learn a whole different thing. We have to learn about canceling, which is an algebra thing. And we don't really want to learn algebra. We're just here to learn basics. We're just here to learn basics. And exponents, we just got to learn basics thing about exponents. It's that they essentially got these things going on. Which means we learned everything we need to learn about. So, yeah. That's it. I'm going to talk about one last thing, and that's about it. And that is... yeah, that's literally what to talk about here. I think that's all the basic stuff. I mean, there's sine, cosine, which is a geometry thing, which also relates with tangent. You may have seen these before. This is geometry terms. Maybe I'll do this another time. But that's really all there is to explain. I think I explained everything I need to do in less than 7 days. I think this might be our last lesson. I think... No. I thought this would be a 7-day experiment. That's everything that's basic about math. I mean, I could talk about negative numbers. I mean, that is a thing I just briefly discussed and touched up upon, saying it's a flow of the direction, where you can go left or right, only left or right. But I think you understand negative numbers if you understand positive numbers. They're not really that different. But I guess I could also talk about imaginary numbers. Impossible numbers. Yeah, I could talk about impossible numbers. Numbers that can't exist. Numbers that just won't work. Alright, so... yeah. Let's try this out. Get a calculator. Any calculator, maybe like the one on your iPhone or on Google, right? And you can type this in. This is a little fun experiment. What number do you get from doing that? Or if you didn't get a number. No, you didn't get a number at all. See, that is the thing about this number here. This number is impossible. It cannot exist. It can't because it's not real. It's imaginary. It's all in your head. Ah, tired. This -1 here is represented in math as I. It is represented as I in this little funny little curvaturing way. But really all it's saying is that there is that here. Because if you have two i's, right next to each other, or I to the second power, or I squared, right? You could essentially just make this equal to -1, which is a nice little rule. Because remember, as I talked about, any square root times another square root will get you whatever is inside the square root. That's what I is. I is a function. I is a variable that's used to temporarily hold this imaginary number in place, so that certain math problems can be solved. This might or might not be useful if you're doing a quadratic formula. Alright, quadratic formula, not quadratic formula. But that's another thing that's complicated, and that's like an algebra 2 thing. I got it. Next class, we'll touch on about algebra. That's what we'll be doing next class. Yes, we'll do a little bit of algebra. Just a little bit. Not too much of it, just a little bit. But we talk about a thing called f of x and x. See you guys then.